Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. There is a field somewhere on Earth. Perhaps you know one like it. The grass is tall enough to whisper in the evening breeze, and the sky above stretches out in every direction, unbounded and impossibly deep. On a night when the moon is new and the air is clear, you can lie on your back in that field and see what our ancestors saw. Thousands upon thousands of points of light, scattered across the darkness, like seeds thrown across black soil. If you stay there long enough, your eyes adjust. The stars multiply. The Milky Way reveals itself as a river of light flowing overhead, and you begin to feel something ancient stirring in your chest. It is not quite longing. It is not quite fear. It is something older than words. A feeling that has lived in human hearts since the first person looked up and wondered what those lights were and whether they could ever be touched. Imagine, for a moment, that you are lying in that field tonight. You are young. Your whole life stretches ahead of you, like an unwritten story. And as you stare at those distant suns, a question forms in your mind, simple and profound. If I could leave Earth right now, if I could point myself toward the stars and travel for my entire lifetime, never stopping, never turning back, how far could I actually go? Not in imagination, not in dreams or science fiction stories, but in reality, according to the laws of physics as we understand them, according to the limits of energy, time, and the fragile biology of the human body. How far? The question sounds simple, but the answer will take us on a journey through the deepest principles of the universe. We will need to understand time itself and how it can bend and stretch. We will need to confront the vast, almost incomprehensible distances between the stars. We will need to reckon with the speed of light, that ultimate cosmic boundary that nothing can cross. And we will need to face the uncomfortable truth that the universe is not built for creatures like us, with our brief spans of consciousness and our delicate, water-filled bodies. But before we can answer this question, we need to understand something fundamental. We need to understand just how short a human lifetime really is, when measured against the scale of the cosmos. We need to understand that when we talk about traveling through space, we are not talking about crossing a room. or even crossing a continent. We are talking about crossing an ocean so vast that light itself, the fastest thing we know, takes years to swim from shore to shore. So let us begin there, in the most unlikely place, with ourselves, with the brief, brilliant flicker of consciousness that we call a human life. If you are fortunate, if medicine and circumstance smile upon you, you might live 80 years, perhaps 90, in rare cases, a century. These feel like long spans of time. When you are living them, childhood stretches on forever. Summers are endless. Even a single year can contain lifetimes of experience, whole chapters of growth and change and transformation. But place that human lifetime against the timescales of the universe, and something strange happens. It doesn't just shrink, it almost disappears. Consider the light leaving the sun right now. This very instant takes about 8 minutes and 20 seconds to reach Earth. 8 minutes. In that time, you might make a cup of coffee. You might walk to a nearby store. You might listen to 2 or 3 songs. And in that same span of time, light crosses the 150 million kilometers between our star and our world, traveling at a speed so extraordinary that nothing in our everyday experience can help us comprehend it. Light moves at roughly 300,000 kilometers per second. To put that in perspective, in 1 second, light could circle the entire Earth more than 7 times. In 1 second. By the time you finish reading this sentence, light will have traveled far enough to loop around our planet dozens and dozens of times. Now think about the moon, that pale companion that hangs in our night sky, close enough that we can see its craters with simple binoculars, near enough that human beings have walked on its surface. The moon sits about 384,000 kilometers away from Earth. Light covers that distance in roughly 1¼ seconds. One blink, and light has made the journey. But let us go a bit farther. Mars, our neighboring planet, the one that glows red in the evening sky and stirs our dreams of exploration. When Mars is at its closest approach to Earth, light takes about 3 minutes to travel between the two worlds. When Mars is on the far side of its orbit, on the opposite side of the Sun from us, that light travel time stretches to about 22 minutes. These numbers begin to hint at something important. Even within our solar system, even among our closest planetary neighbors, distances are measured not in the time it takes to drive or fly, but in the time it takes for light itself to cross the gap. And light, remember, is the fastest thing that exists. Jupiter, the giant of our solar system, that vast world of storms and moons, sits roughly 40 to 50 light minutes away, depending on where Earth and Jupiter are in their orbits. Saturn, with its magnificent rings, is about an hour and a quarter of light travel time from the Sun. These are not places you can visit on a weekend trip. These are distances that dwarf anything in our terrestrial experience. And yet, and this is crucial to understand, all of these planets, these worlds that seem so impossibly far away, are all in our immediate cosmic neighborhood. They are all within a single solar system. They are all bound to the same star, all orbiting within a region of space that, cosmically speaking, is incredibly tiny, because beyond Saturn, beyond even the ice giants Uranus and Neptune, beyond the scattered rocks and ice balls of the Kuiper Belt, beyond even the vast sphere of comets that we call the Oort cloud, beyond all of that lies something we can barely conceive of. Interstellar space, the space between the stars. And those distances are not measured in light minutes or even light hours. They are measured in light years. A light year is the distance light travels in one Earth year, not 1 second, not 1 day, 1 full year, 300,000 kilometers per second, every second, for an entire year. When you calculate that distance, you get a number so large, it becomes almost meaningless. About 9.5 trillion kilometers. 9 trillion, 500 billion. A number our brains are not equipped to grasp. And the nearest star to our Sun, a small red dwarf called Proxima Centauri, sits more than 4 light years away. So when we ask how far a human could travel in one lifetime, we are asking something profound. We are asking what a span of 80 or 90 years means. Against these distances, we are asking what is possible when the very fabric of space is so vast and our lives are so brief. An 80-year human lifetime is about 2.5 billion seconds. It sounds like a lot, but light, in that same span of time, travels about 80 light years, which means that even light, the fastest possible thing, moving at the cosmic speed limit for an entire human lifetime, would cross only a tiny fraction of our galaxy. The Milky Way is about 100,000 light years across. Light itself, traveling for a human lifetime, would cross less than 1/10% of our galaxy's width. This is what we are up against. This is the reality we must face if we want to understand the question. Space is not just big. It is big in a way that makes human scales of time and distance seem like whispers in a thunderstorm. And we, with our brief lives, And our slow machines are trying to find out how far we can go. Let us start with what we have already done. Let us start with our first tentative steps away from home. On July 20, 1969, two human beings stood on the surface of another world for the first time in our species' history. Neil Armstrong and Buzz Aldrin climbed down a ladder from their lunar module and walked on the moon. They spent about 2.5 hours outside, collecting rocks, taking photographs, planting a flag, and staring back at the blue marble of Earth, hanging in the black sky. The distance they had traveled was 384,400 kilometers. The journey had taken about 3 days. Think about that for a moment. 3 days to reach the closest natural object to Earth beyond our own planet. 3 days of travel at tremendous speeds, powered by the most powerful rocket ever built, the Saturn V, which stood taller than a 36-story building and burned fuel at such a furious rate that its engines consumed tonnage per second. The Apollo astronauts traveled at speeds reaching about 11 kilometers per second during parts of their journey. 11 kilometers every second. That is roughly 40,000 kilometers per hour. Fast enough to cross the United States in about 6 or 7 minutes. Fast enough that the human mind cannot process the speed in any meaningful, experiential way. And yet, even at that extraordinary velocity, it took 3 days to reach the moon. After the Apollo program ended in 1972, humanity did not return to the moon. We built space stations instead. We created the International Space Station, a laboratory that orbits Earth at an altitude of about 400 kilometers, traveling at approximately 7.5 kilometers per second. The astronauts aboard the ISS are genuinely in space, experiencing weightlessness, watching Earth spin below them, completing an orbit every 90 minutes or so. But they are still, in cosmic terms, right next to Earth. 400 kilometers is about the distance from London to Edinburgh, or from New York to Boston. They have not left Earth's immediate vicinity. They are, metaphorically speaking, still standing in the front yard. If we want to know how far humans have actually sent something, anything, from Earth, we need to talk about the Voyager spacecraft. Voyager 1 and Voyager 2 launched in 1977, nearly 50 years ago. As of now, they were designed to take advantage of a rare alignment of the outer planets, a geometric configuration that occurs only once every 176 years. This alignment allowed the spacecraft to use gravity assists, essentially stealing a tiny bit of momentum from each planet they visited, slingshotting themselves faster and farther. With each encounter, Voyager 1 visited Jupiter and Saturn. Voyager 2 visited all 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. And then, their planetary tours complete, they continued outward into the darkness beyond. As of 2025, Voyager 1 is more than 24 billion kilometers from Earth. That is about 160 times the distance from Earth to the Sun. It has crossed into interstellar space, passing beyond the region where the Sun's solar wind dominates, entering the space between stars, 24 billion kilometers in nearly 50 years. Let that sink in. Nearly 5 decades of continuous travel, never slowing down, never stopping. And Voyager 1 has covered about 24 billion kilometers. That sounds enormous. And it is enormous. By human standards, it is the farthest any human-made object has ever traveled. But in cosmic terms, Voyager 1 has barely left the neighborhood. Remember that Proxima Centauri, the nearest star, is about 4 light-years away. 4 light-years is roughly 38 trillion kilometers. Voyager 1, traveling at about 17 kilometers per second, would take more than 70,000 years to reach Proxima Centauri. 70,000 years. The entirety of recorded human history is only about 5,000 years old. Our species has only existed for perhaps 300,000 years. Voyager 1, at its current speed, would need a span of time longer than human civilization has existed just to reach the very first star beyond our sun. This is the brutal arithmetic of interstellar space. This is the reality that confronts us when we ask how far a human could travel in one lifetime. We have built the fastest machines we know how to build, and they are still achingly, impossibly slow when measured against the distances we want to cross. But perhaps we are thinking about this wrong. Perhaps the problem is not how far we have gone, but how fast we are going. Perhaps if we could just move faster, the question would change. Perhaps if we could approach the cosmic speed limit, the ultimate velocity, we could finally cross the distances that separate the stars. Let us talk about that speed limit. Let us talk about light. In our everyday lives, we are accustomed to the idea that if you want to go faster, you simply push harder. You want your car to accelerate. You press the gas pedal. You want to throw a ball farther. You throw it harder. Speed, in our normal experience, is something that can always increase. There is no fundamental limit. There is just the practical limit of how much force you can apply. But the universe does not work this way. There is a maximum speed, a cosmic speed limit, written into the very fabric of reality. And that speed is the speed of light, approximately 299,792,458 meters per second. Usually, we round this to 300,000 kilometers per second. For simplicity, this is not just fast. This is, as far as we understand the universe, the fastest that anything can go. Not the fastest we have made something go. Not the fastest we theoretically could make something go. With better technology, the fastest that anything, even in principle, can travel through space. Why? Why should there be a speed limit at all? The answer lies in the nature of space and time themselves. In Einstein's theory of special relativity, and while the mathematics of relativity can be complex, the core idea is surprisingly elegant. Mass and energy are related. In fact, they are different forms of the same thing. This is what Einstein's famous equation, E equals mc squared, tells us. Energy equals mass times the speed of light squared. And because the speed of light is such an enormous number, even a tiny amount of mass represents a tremendous amount of energy. Now, when you try to accelerate something, when you try to make it go faster, you are adding energy to it. And here is where things get strange. As an object with mass goes faster and faster, approaching the speed of light, the energy required to accelerate it further increases, not linearly, exponentially. Imagine trying to push a boulder up a hill. At first, it is hard, but manageable. You lean into it, you push, and it moves. Now imagine that as you push, the boulder gets heavier. Not just a little heavier, dramatically, exponentially heavier. The closer you get to the top of the hill, the heavier the boulder becomes, until it would weigh more than the entire Earth, more than the entire solar system, more than anything. This is what happens when you try to accelerate something with mass to the speed of light. The closer you get to light speed, the more energy you need to add to go even a tiny bit faster. And as you approach the speed of light, the energy required approaches infinity. Infinity, not a large number, not a number we haven't figured out how to produce yet. Infinity, which means it is impossible. You cannot accelerate mass to the speed of light. Because you would need infinite energy. And infinite energy does not exist. Light itself can travel at light speed only because photons, the particles of light, have no mass. They are pure energy. They are born, moving at the cosmic speed limit, and they have no choice but to move at that speed for as long as they exist. But anything with mass, anything physical, anything you could build a spacecraft from, can only approach the speed of light. It can get closer and closer. 99% of light speed, 99.9%, 99.99%. Each step requiring exponentially more energy than the last. But it can never quite reach it. This is not a technological problem. This is not something we can solve with cleverer engineering or better materials. This is a fundamental law of the universe. The speed of light is the speed limit, not because we haven't found a way around it yet, but because there is no way around it. It is woven into the structure of space-time itself, and this has profound implications for our question, because if we want to travel far in one lifetime, we need to travel fast. And if there is a hard limit on how fast we can go, then there is, by extension, a hard limit on how far we can go, unless there is something else we can use, some principle or loophole or strange consequence of physics that might help us. And remarkably, there is. But before we explore that, we need to understand where we are right now. We need to understand how fast we can actually go with the technology and physics we currently understand. The rockets that took Apollo astronauts to the moon were chemical rockets. They burned fuel mixed with an oxidizer in a controlled explosion, and the expanding gases shot out the back of the rocket at tremendous speeds, pushing the rocket forward through Newton's third law. For every action, there is an equal and opposite reaction. These chemical rockets were, and still are, engineering marvels. The Saturn V rocket could produce over 7 million pounds of thrust. The space shuttle's main engines could burn through 500,000 gallons of fuel in just 8.5 minutes. The forces involved, the precision required, the sheer violence of controlled combustion necessary to lift tens or hundreds of tons of metal and fuel into space is extraordinary. But chemical rockets have a fundamental limitation. They are slow. The Apollo spacecraft reached speeds of about 11 kilometers per second. The space shuttle orbited at about 7.5 kilometers per second. These are incredible velocities by human standards. But remember, the cosmic speed limit 300,000 kilometers per second. The fastest chemical rockets we have built travel at about 0.0000367 times the speed of light. Not even close to 1%. Not even close to 1/10%. In recent years, we have developed faster spacecraft by using gravity assists and purpose-built missions. The Parker Solar Probe, designed to study the Sun up close, has reached speeds of about 192 kilometers per second during its closest approaches to the Sun. That is more than 17 times faster than Apollo. It is, as of now, the fastest human-made object ever created. But even at 192 kilometers per second, the Parker Solar Probe is moving at only about 0.064% of light speed. Still not even close to 1%. New Horizons, the probe that flew past Pluto in 2015, traveled at about 16 kilometers per second. Fast enough to cross the United States in about 5 minutes. But again, only about 0.0053% of light speed. Chemical rockets, it turns out, can only take us so far. And the reason is simple. Rockets have to carry their fuel with them. The more fuel you carry, the heavier your rocket is. The heavier your rocket is, the more fuel you need to accelerate it. This creates a vicious cycle, a tyranny of mass and energy. That makes it extraordinarily difficult to reach high speeds. So scientists and engineers have imagined alternatives. One concept is nuclear propulsion. Instead of burning chemical fuel, you use the heat from nuclear reactions to heat a propellant, usually hydrogen, and expel it at very high speeds. This can produce much higher exhaust velocities than chemical rockets, which means better efficiency. Project Orion, conceptualized in the 1950s and 1960s, imagined a spacecraft pushed forward by nuclear explosions, detonated behind a massive pusher plate, literally riding the shock waves of atomic bombs. The mathematics suggested it could work. A spacecraft powered by nuclear pulse propulsion could potentially reach velocities of a few percent of the speed of light. 2, maybe 3%. That is hundreds of times faster than our current chemical rockets. But Project Orion was never built. The technical challenges were enormous. The political will was absent, and nuclear test ban treaties made it effectively impossible to develop. Still, it showed that higher speeds were theoretically possible. Ion drives, which use electric fields to accelerate ions and create thrust, are another option. They are incredibly efficient, but they produce very low thrust. An ion drive generates about as much force as the weight of a piece of paper. pressing on your hand, but in the vacuum of space, where there is no friction, even a tiny continuous thrust, applied over months or years, can accelerate a spacecraft to high speeds. The Dawn mission, which explored the asteroid Vesta and the dwarf planet Ceres, used ion propulsion. Over the course of its mission, it changed its velocity by more than any spacecraft in history, achieving a delta V of over 11 kilometers per second through continuous, patient acceleration. But even ion drives, running for decades, would struggle to get us to a significant fraction of light speed. The power requirements would be immense, and the travel times would still be measured in thousands of years. For interstellar journeys, fusion rockets, which would use the same process that powers the sun, fusing hydrogen into helium and directing the resulting energy as thrust, have been theorized for decades. If we could build them, they might reach 10 to 15% of light speed, maybe even 20% in the most optimistic scenarios. But we cannot build them yet. We have not even achieved sustained net positive fusion reactions here on Earth, much less miniaturized the technology and made it reliable enough for a spacecraft. So here's where we stand. With our current flight-proven technology, we can travel at speeds of about 10 to 20 kilometers per second, sustained over years. With optimistic near-future technology, nuclear pulse propulsion, or fusion rockets, we might reach a few percent of the speed of light, maybe 5%, maybe 10%, if we are very fortunate and very clever. At 10% of light speed, a journey to Proxima Centauri would take about 42 years. That is within a human lifetime. Just barely. You would have to leave Earth as a young adult and arrive in your 60s, having spent your entire adult life in a spacecraft. But even that assumes we can build a propulsion system that can sustain 10% of light speed, which we cannot do yet. And it assumes we can solve the problems of food, water, radiation shielding, psychological health, and all the other challenges of keeping a human being alive and sane in a tiny metal box for 4 decades. The reality is this: with the physics we understand and the technology we currently have or can plausibly develop, in the near future, we can travel fast enough to explore our solar system in years or decades. But the stars remain achingly, brutally far away. So let us ask a different question. Let us make the calculation explicit. If you As a human being, left Earth today, on the fastest spacecraft we could reasonably build, in the next few decades, where could you go before your life ran out? Let us imagine you are 25 years old. You are in good health, and with medical advances, you might reasonably expect to live another 80 years, perhaps to the age of 105. That gives you 8 decades of travel time, 80 years, to go as far as you possibly can. We will start with current technology, the speeds we know we can achieve, and then we will move to optimistic projections with current chemical rocket technology. Sustained speeds of about 15 to 20 kilometers per second are realistic for long-distance missions. Let us use 17 kilometers per second, roughly the speed of Voyager 1. In 80 years, at 17 kilometers per second, you would travel about 43 billion kilometers. That is about 287 times the distance from Earth to the Sun. It would take you well beyond Neptune's orbit, which is about 30 times the Earth-Sun distance. You would cross the Kuiper Belt, that region of icy bodies beyond Neptune, where Pluto resides. You would even begin to enter the scattered disk, the region of space, where objects have highly elliptical orbits, flung outward by gravitational interactions with the giant planets. Long ago, but you would not reach the Oort cloud. The inner edge of the Oort cloud is thought to begin at about 2,000 times the Earth-Sun distance, and the outer edge may extend 50,000 times that distance. At current spacecraft speeds, you would not even reach the beginning of the Oort cloud. In a human lifetime, you would, however, have truly left the planets behind. You would be in deep space, the space between our solar system and the stars, surrounded by darkness and silence, with the sun shrunk to just another bright star behind you. Now, let us be more optimistic. Let us imagine that in the next few decades, we develop nuclear pulse propulsion or an advanced fusion rocket. Let us imagine you can travel at 5% of the speed of light. 5% of light speed is about 15,000 kilometers per second, roughly 1,000 times faster than Voyager. At that speed, in 80 years, you would travel about 4 light years. For light years, do you see what just happened? At 5% of light speed, a velocity that would require technology we do not yet possess. Technology that would represent one of the greatest engineering achievements in human history. You would travel for your entire lifetime and reach Proxima Centauri. Just barely. You would arrive at the nearest star to our Sun, 4.24 light-years away. In your very old age, having spent every year of your adult life in transit, you would never see Earth again. You would never feel rain, or wind, or grass beneath your feet. You would grow old in a spacecraft, watching Proxima Centauri grow brighter and brighter through the window, year after patient year. And that is assuming everything went perfectly, assuming your spacecraft did not break down, assuming you did not succumb to radiation or illness, assuming your mind did not fracture from the isolation and the monotony and the sheer existential weight of being the first human to travel to another star. Let us push even further. Let us imagine 10% of light speed. At that velocity, you could reach Proxima Centauri in about 42 years. You could launch at age 25 and arrive at age 67. You would still be alive. You would see another star up close. You might even have time to explore whatever planets orbit it, to send your findings back to Earth, to know that you had done something no human had ever done before. But even that assumes we can build a propulsion system capable of sustained 10% light speed, which is far beyond our current capabilities. It assumes we can shield the spacecraft from interstellar dust and gas, which at those speeds would hit like bullets. It assumes we can generate or carry enough energy to accelerate to that speed and then decelerate again at the destination. And even if we solve all of those problems, 10% of light speed gets you to exactly one star. In a human lifetime, there are roughly 400 billion stars. In our galaxy, you could reach one of them. This is the hard truth. This is the calculation that confronts anyone who dreams of exploring the stars. Space is so vast, and our speeds are so slow, and our lives are so brief, that even our best-case scenarios leave us trapped in our immediate cosmic neighborhood. But there is something we have not discussed yet. Something strange and beautiful and deeply counterintuitive. Something that might, just might, change the equation. We need to talk about time. Actually, let me correct that section heading. We have already talked about the speed limit. What we need to talk about now is what happens to time when you approach that limit. Because here's the thing about special relativity. The thing that seems like science fiction, but is absolutely, experimentally verified reality. Time is not absolute. It is not the same for everyone. It depends on how fast you are moving. If you are sitting still or moving slowly, time passes normally. 1 second per second, 1 year per year. But as you begin to move faster, as you approach the speed of light, time for you begins to slow down relative to the rest of the universe. This is not an illusion. This is not a trick of perception. This is actual physical time dilation. Let us use an example. Imagine two twins, identical in every way. One stays on Earth. The other boards a spacecraft and accelerates to 90% of the speed of light, travels to a nearby star, turns around, and comes back at the same speed. When the traveling twin returns, they will be younger than the twin who stayed behind. Not metaphorically younger, not younger in spirit or health. Actually, physically, biologically younger. Fewer years will have passed for them. Their cells will have divided fewer times. Their heart will have beaten fewer beats. This is called the twin paradox. Though it is not really a paradox, it is simply what happens when you move at relativistic speeds, at 90% of the speed of light. Time passes at about 44% of the normal rate. For every year that passes on Earth, only about 5 months pass for the traveler. At 99% of light speed, time slows to about 14% of normal. 1 year on Earth equals about 1.5 months for the traveler. At 99.9% of light speed, the dilation becomes extreme. Time passes at about 4.5% of normal. 22 years on Earth equals 1 year for the traveler. Do you see the implication? If you could travel fast enough, if you could reach a significant fraction of light speed, you could travel much farther than we have been calculating. Because even though the universe would age normally, even though Earth and everyone you knew would grow older at the usual rate, time for you, the traveler, would slow down. You could cross distances that would normally take centuries and experience only decades at 99.99% of the speed of light. Time dilation becomes even more pronounced. At that speed, you could travel 100 light years and experience only about 1 year of travel time. You could cross our entire galaxy, 100,000 light years, in what would feel like about 1,000 years to you. Still a long time, still beyond a single human lifetime, but no longer beyond the reach of human timescales, no longer beyond the reach of many generations. This sounds like a loophole. It sounds like a way to cheat the brutal arithmetic of cosmic distances. And in a sense, it is. Time dilation is real. It could allow a traveler to cross vast distances within their subjective lifetime. But there is a cost, a terrible cost. First, the energy required to reach these speeds is staggering. Remember, as you approach light speed, your effective mass increases. The energy needed to accelerate you further grows exponentially to reach 99% of light speed. You would need energy equivalent to about 7 times your rest mass. At 99.9%, it is about 22 times your rest mass. At 99.99%, about 70 times. We are talking about energies that dwarf anything humanity has ever produced. We are talking about harnessing the power of stars. Second, and perhaps more heartbreaking, everyone you know would be gone. If you left Earth at age 25, traveled at 99% of light speed to a star 50 light years away, and then returned, you would experience only about 7 years of travel time. You would return at age 32, but on Earth, 100 years would have passed. Everyone you knew would be dead. The world would be unrecognizable. You would be a stranger from the past, stepping into a future you never saw coming. This is the price of relativistic travel. You can go far. You can experience the journey in a reasonable span of time. But you can never go home. Not to the home you left. That place, those people, would exist only in memory. And there is a third problem, perhaps the most fundamental. We do not know how to reach these speeds. We have theories, concepts, ideas scribbled on whiteboards and published in papers. But we do not have the engineering. We do not have the energy sources. We do not have the materials that could withstand the acceleration, or the cosmic radiation, or the impacts with interstellar dust. At such velocities, time dilation is real. It is beautiful. It offers a glimpse of how the universe could be explored, how distances could be crossed. But it does not change the fundamental challenge. It shifts the problem from the distances are too great to the speeds are too difficult. And we are still left with the question, in one human lifetime, with one human body, born and raised in the gentle gravity and warm atmosphere of Earth, how far could you actually go? To answer that, we need to think about other possibilities, other ways of extending the journey. If the problem is that human lives are too short and spacecraft are too slow, then perhaps the answer is not to make the spacecraft faster. Perhaps the answer is to make the lives longer, or to string many lives together. This is the idea behind generation ships. Vast spacecraft, self-contained and self-sustaining, carrying not just a crew, but an entire community. The people who launch the ship know they will never reach the destination. Their children will not reach it either, nor their grandchildren, but perhaps their great-great-great-grandchildren. Generations hence, will arrive at a new star, having been born and raised entirely in space, carrying forward a mission they inherited. The concept is romantic in a way. An arc through the stars, a closed ecosystem drifting through the void, maintaining itself, recycling water and air, growing food, raising children, passing down stories of Earth. The blue world no one aboard has ever seen, except in photographs. But the reality would be extraordinarily challenging. First, you would need a ship large enough to support a stable population. Not a dozen people, not even 100. You would need hundreds, perhaps thousands, to ensure genetic diversity, to prevent inbreeding, to maintain a functioning society. That ship would need to be enormous. It would need farms, or at least advanced hydroponics. It would need water recycling systems that never fail. It would need power, probably from nuclear reactors, running continuously for centuries. It would need to be able to repair itself, to replace broken parts, to manufacture new components from raw materials carried along, and it would need to maintain social cohesion. This is perhaps the hardest part. Imagine being born on a spacecraft, knowing you will live your entire life in a metal tube, knowing you will never set foot on a planet, never see an open sky. Imagine the psychological toll. Imagine the temptation to give up, to turn back, to abandon a mission that has already consumed generations and will consume generations more. There have been studies, thought experiments, simulations, and the conclusion is always the same. Generationships are possible in principle, but the challenges are as much human and social as they are technical. An alternative, equally speculative, but perhaps more tractable, is suspended animation, cryosleep. The idea that you could freeze a human body, or at least slow its metabolism to an imperceptible crawl, and then wake it up decades or centuries later, biologically unchanged. We can freeze cells. We can freeze embryos. We can even freeze small organisms, like nematode worms, and revive them. But freezing a human body is vastly more difficult. The problem is ice. When water freezes, it forms crystals, and those crystals expand inside a cell. Ice crystals can puncture the cell membrane, shredding the delicate structures that keep the cell alive. Freeze a human body, and you are essentially shredding trillions of cells from the inside out. Some animals, like wood frogs and certain insects, can survive freezing because they produce antifreeze proteins, substances that prevent ice crystals from forming or limit their size. But humans do not have this ability. We are warm-blooded creatures, evolved to maintain a constant temperature, not to endure freezing. There are techniques being explored. Vitrification, for example, where the body is infused with cryoprotectants, chemicals that prevent ice formation, and then cooled to temperatures where molecular motion essentially stops, but no ice crystals form. The body becomes a glass-like solid, biologically inert. but structurally intact. In theory, a vitrified body could be stored indefinitely and then warmed and revived. In practice, we have never done this with anything larger than a rabbit kidney. The technical challenges are immense. The margin for error is zero. A single mistake during the freezing or warming process, a single ice crystal forming in the wrong place, could cause irreparable damage. And even if we could perfect cryopreservation, even if we could freeze and revive a human being safely and reliably, there is still the question of the journey. Who operates the ship while you sleep? Do you trust automated systems to run for decades or centuries without failure? Do you have a crew that takes shifts? Some awake, some frozen, rotating through the years. All of these ideas, generation ships, and cryosleep, and the variations in between, share a common thread. They are attempts to extend human presence beyond the single lifetime. They are acknowledgments that the stars are so far away that one life is not enough. But they do not change the original question. They change the rules. If you can freeze yourself, if you can sleep for centuries, then your subjective experience of time is no longer bound to your biological age. The journey might take 500 years, but if you sleep through it, those 500 years cost you nothing. You board the ship young, you wake up young, and the distance has been crossed. But that is not traveling in one lifetime. That is traveling across many lifetimes of elapsed time, compressing them into the experience of a single consciousness. The question we are asking is different. The question is, if you lived one normal, biological, continuously conscious human lifetime, never sleeping for centuries, never passing the journey to your descendants, how far could you go? And to answer that, we need to understand not just the physics of travel, but the biology of the traveler. Space, for all its beauty and mystery, is not a place where humans belong. We are creatures of Earth. We evolved under gravity, surrounded by air, protected by a magnetic field, and an atmosphere that shields us from radiation. We are adapted to warm sun on our skin, to water and food freely available, to microbes and bacteria that live in symbiosis with us. In space, all of that goes away. On the International Space Station, astronauts experience microgravity, or what is commonly called weightlessness. Their bodies float. They can push off walls and drift across the cabin. It looks effortless and graceful, and it is, for a time. But the human body interprets weightlessness as a problem. On Earth, your bones and muscles must constantly work against gravity. When you stand, your legs support your weight. When you lift your arm, your muscles work to overcome the pull of Earth. This constant resistance keeps your bones dense and your muscles strong. In microgravity, that resistance vanishes. Your body decides it no longer needs strong bones or large muscles. Why maintain what is not being used? So it begins to dismantle them. Astronauts on the ISS lose bone density at a rate of about 1 to 2% per month, mostly in the legs, hips, and spine, the weight-bearing bones. After 6 months in space, an astronaut can lose as much as 10% of their bone mass. Muscles atrophy as well, even with rigorous daily exercise. Several hours a day of resistance training on specialized equipment, astronauts lose muscle mass. The muscles in the legs and back, the ones that do the most work on Earth, shrink the fastest. When astronauts return to Earth after long missions, they often cannot walk immediately. They have to be carried out of the spacecraft. It takes weeks or months of rehabilitation to regain strength and balance. Now imagine a journey, not of 6 months, but of decades. Imagine trying to maintain your body through 50, 60, 70 years of weightlessness, even with perfect exercise regimens, even with advanced medical interventions. The human body was simply not designed for this. And then there is radiation. On Earth, we are protected by 2 things: the atmosphere and the magnetic field. The atmosphere absorbs and scatters most of the harmful radiation from the sun and from deep space. The magnetic field deflects charged particles, the solar wind, sending them spiraling around the planet, rather than crashing into the surface. In space, you have neither cosmic rays, high-energy particles from distant supernovae and other violent cosmic events pass through spacecraft walls as if they were paper. They pass through your body, ionizing atoms, breaking chemical bonds, damaging DNA. The damage is cumulative. A little bit each day, a little bit each week, over years and decades. The risk of cancer increases, the risk of cataracts, the risk of neurological damage. Some cosmic rays are so energetic that astronauts report seeing flashes of light when they close their eyes, the particles zipping through their retinas and triggering signals in the optic nerve. On the ISS, orbiting inside Earth's magnetic field, astronauts are partially protected, but on a journey to another star, far from Earth, far from any planet's magnetic field, the radiation exposure would be relentless. You could shield the spacecraft, line it with water, or polyethylene, or lead. But shielding is heavy, and heavy means harder to accelerate, harder to move. There is always a trade-off between protection and practicality. And even if you solve bone loss and muscle atrophy, and radiation. There are other challenges: isolation, confinement, the psychological strain of being trapped in a small space with the same few people, or perhaps completely alone, for decades on end. Human beings are social creatures. We need connection, novelty, purpose. We need to feel that our lives have meaning, that our actions matter. On a decades-long voyage to a distant star, what keeps you going? What gets you out of bed? Metaphorically speaking, when every day is the same as the last, when the destination is still years or decades away, when everyone you ever knew on Earth is aging and changing and living lives you cannot share. There have been psychological studies of isolated groups, Antarctic research stations, submarines, long-duration space missions, and the findings are consistent. People adapt, but it is hard. Conflicts arise. Depression is common. The lack of privacy, the inability to escape, the sheer monotony wears on the human spirit. A journey to the stars would test not just our technology, but our humanity. It would test whether we are capable, psychologically and biologically, of enduring the voyage. And this brings us back to the central question: even if we could build a spacecraft capable of reaching a significant fraction of light speed, even if we could solve the energy requirements, the propulsion challenges, the engineering hurdles, could we actually put a human being inside it and expect them to survive? Could a human body, with all its fragility and needs and evolutionary baggage, actually make the journey? The answer, based on what we know now, is uncertain. It would be extraordinarily difficult. It would require medical advances we do not yet have, psychological support systems we have not yet designed, life support technologies that can run flawlessly for decades. But perhaps it is possible. Perhaps, with enough care and preparation and innovation, a human could cross the distance to a nearby star and arrive still alive, still sane, still recognizably human. But we have been thinking of this journey in terms of distance and speed. We have been asking how far you could go in one lifetime, measured in light years or kilometers. There is another way to think about it, another boundary that limits how far we can travel. And that boundary is not distance or speed. It is the universe itself. For most of human history, we thought the universe was static, unchanging. The stars might move relative to each other, orbits might shift, but the overall structure, the fabric of space itself, was fixed. We were wrong. In the 1920s, an astronomer named Edwin Hubble made a discovery that would reshape our understanding of the cosmos. He observed distant galaxies and noticed something strange. They were all moving away from us. And not just moving, but receding. The farther away a galaxy was, the faster it was receding. This was not because we were at the center of some cosmic explosion. This was because space itself was expanding. Every point in the universe is moving away from every other point, like dots on the surface of a balloon being inflated. The fabric of space is stretching, carrying galaxies along with it. This means the universe had a beginning. If everything is moving apart now, then in the past, everything was closer together. Go back far enough, and everything in the observable universe was compressed into an infinitesimally small point. This moment, this beginning, is what we call the Big Bang, though that name is somewhat misleading. It was not an explosion in space. It was an expansion of space itself. The universe is about 13.8 billion years old. That is how long space has been expanding. And it is still expanding now. And it will continue to expand for as far into the future as we can predict. Here is the strange and unsettling consequence of this. There are galaxies so far away that the space between us and them is expanding faster than light can cross it. Light leaving those galaxies right now will never reach us, not because the light is slow, but because the space itself is stretching faster than the light can traverse. This creates a boundary, a cosmic horizon, beyond a certain distance, roughly 46 billion light years. In any direction, objects are receding from us faster than the speed of light. They are not actually moving through space faster than light, which would violate relativity. But the expansion of space itself carries them away from us at superluminal speeds. And here is the truly sobering part. As the universe continues to expand, as the rate of expansion accelerates, a process driven by something we call dark energy, more and more galaxies will cross this horizon. They will move beyond the edge of the reachable universe. Right now, most of the galaxies we can see are still within the reachable part of the universe. If we could travel at the speed of light, we could eventually reach them, given enough time. But billions of years from now, if the expansion continues, those galaxies will have receded beyond the horizon. Even light will not be able to reach them. This means there is a fundamental limit to how much of the universe we, or any future civilization, could ever explore, not because of our technology, not because of the fragility of our bodies, or the shortness of our lives, but because the universe itself is structured in a way that makes some regions forever unreachable. Even if we became immortal, even if we solved every engineering challenge, Even if we could travel at the speed of light for billions of years, there would still be galaxies, billions upon billions of galaxies, that we could never visit. And this brings a strange kind of perspective to our original question. We have been worrying about whether we can travel a few light years in a human lifetime, whether we can reach the nearest star, whether our biology and our physics will allow us to cross even the smallest interstellar distances. But even if we succeed, even if we become a spacefaring civilization, even if our descendants spread across the galaxy and then beyond, there will always be limits. There will always be horizons we cannot cross. The universe is vast, but it is also, in a very real sense, bounded, not by walls or barriers, but by the expansion of space itself. Still, we have not yet answered the practical question, the immediate question, not what future civilizations might do, but what you, a single human, living now, could do if you left Earth tomorrow on the best spacecraft we could build, with the best technology we could plausibly develop. Where would you be when your life ended? Let us return to the tangible. Let us talk about energy. Underneath all of our limitations, underneath the fragility of the human body, and the vastness of space, and the speed of light, and the expansion of the universe, there is one fundamental constraint that shapes everything: energy. Moving through space requires energy. The faster you want to go, the more energy you need. The more mass you want to move, the more energy you need. And there is no way around this. It is written into the laws of physics. Let us put some numbers to this. Let us imagine you want to send a spacecraft weighing 1,000 kilograms, about the mass of a small car, to Proxima Centauri at 10% of the speed of light. First, you need to accelerate that spacecraft to 10% of light speed. The kinetic energy of an object is 1/2 its mass times its velocity squared. At 10% of light speed, that is roughly 4.5 times 10 to the 17th joules. To put that in perspective, that is about 112 million terajoules. The entire energy consumption of humanity in a year is about 600 exajoules, or 600 million terajoules. So to accelerate a 110 spacecraft to 10% of light speed, you would need about 1/5 of the total energy humanity uses in an entire year for a single spacecraft weighing 1 ton. And that is just to accelerate it. If you want to stop when you get there, if you want to actually explore the destination, rather than just fly past it, you need to decelerate. That requires just as much energy. So you are looking at 2/5 of humanity's annual energy consumption just to send a tiny 1-ton probe to the nearest star. Assuming perfect efficiency, which does not exist. Now imagine trying to send a spacecraft large enough to carry a human being. You would need life support, radiation shielding, food and water for decades, medical equipment, living space. A human-carrying spacecraft would mass tens or hundreds of tons, not 1 ton. The energy requirements scale linearly with mass. A 100-ton spacecraft would require 100 times as much energy. You are now talking about energy scales that dwarf anything humanity has ever harnessed. And this assumes you can convert energy into kinetic energy with perfect efficiency, which you cannot. Rockets are inefficient. They expel mass to generate thrust, and much of the energy goes into accelerating the expelled mass, not the spacecraft. Even the most efficient theoretical rockets, like photon drives that expel pure light, have limits. The fundamental problem is this: to reach high speeds, you need enormous amounts of energy. And energy in the universe is not infinite. It has to come from somewhere. On Earth, we get most of our energy from the sun. Indirectly, fossil fuels are ancient sunlight, stored in chemical bonds. Solar panels capture sunlight directly. Wind and hydroelectric power are driven by the sun heating the atmosphere and evaporating water. But in space, far from the sun, those sources disappear. You have to carry your energy with you, or generate it on board. Nuclear fission, splitting heavy atoms like uranium, can produce large amounts of energy from relatively small amounts of fuel. Nuclear fusion, combining light atoms like hydrogen, produces even more energy per unit mass. These are the energy sources we would likely rely on for deep space missions. But even fusion, the process that powers stars, has limits. The total amount of energy you can extract from a given amount of fuel is finite, and you have to carry that fuel. The more fuel you carry, the heavier your spacecraft. The heavier your spacecraft, the more energy you need to accelerate it. The more energy you need, the more fuel you must carry. This is the rocket equation, the tyranny of propulsion. It is a vicious cycle that makes high-speed interstellar travel extraordinarily difficult. There are theoretical ways around this. You could build massive lasers in space, powered by the sun or by fusion reactors, and use them to push light sails, thin reflective sheets that gain momentum from light pressure. The spacecraft would not need to carry fuel. It would be accelerated by the laser, reaching high speeds without the tyranny of the rocket equation. But even that requires building the infrastructure. You need enormous lasers, powerful beyond anything we have built. You need them to run continuously for years. You need to aim them precisely across interstellar distances, compensating for the motion of the target spacecraft. and the expansion of space. It could work, in principle, but it would represent an energy expenditure. On a civilizational scale, it would require us to harness not just Earth's resources, but the resources of the solar system. It would require what some have called a Type 2 civilization, one that can harness the entire energy output of a star. We are not there yet. We are barely a Type 1 civilization, one that can harness the energy resources of an entire planet. And this is the true boundary. This is the limit that constrains how far a single human can travel in a lifetime. Not the speed of light, not the fragility of the body, not even the vastness of space. Energy. You can imagine faster rockets. You can imagine cryosleep, or generation ships, or relativistic time dilation. But unless you can solve the energy problem, unless you can find a way to generate or harness amounts of energy that dwarf what we currently use, those technologies remain purely theoretical. This is why, when we calculate how far you could travel in one lifetime, the answer depends not just on your lifespan or the physics of speed, but on what energy sources you have access to. And with the energy sources we have now, or are likely to develop in the near future, the answer is clear. You could explore the solar system. You could visit the outer planets, perhaps even venture into the Oort cloud. But the stars would remain beyond reach unless we stop thinking about one human lifetime, unless we think about many lifetimes strung together across centuries and millennia, unless we think not about what you could do, but what humanity as a whole might one day achieve. Let us step outside the boundary of the question. For a moment, let us imagine not what one person could do in one lifetime, but what a civilization could do across many lifetimes. Imagine that humanity survives, not just survives, but thrives. We solve our problems here on Earth. Climate change, resource depletion, conflict. We develop technologies that allow us to live sustainably, to generate energy cleanly and abundantly, to expand into space, not as a desperate escape, but as a natural next step. Over centuries, we built habitats in orbit. We mine the moon for resources. We extract water from asteroids and metals from the Kuiper Belt. We construct massive solar arrays, capturing energy from the sun. We establish self-sustaining colonies on Mars, on the moons of Jupiter and Saturn, in rotating habitats drifting through the asteroid belt. We become, truly, a spacefaring civilization. And then, slowly, patiently, we begin to look outward. We send probes first, small, robotic, equipped with AI sophisticated enough to repair themselves, to navigate autonomously. to make decisions across light years of communication delay. These probes travel to the nearest stars, not in decades, but in centuries. They arrive, survey the systems, send back data, and then, perhaps, they replicate themselves, building new probes from materials they find, sending those probes to even more distant stars. This is the idea of self-replicating probes, sometimes called von Neumann probes, after John von Neumann, who studied self-replicating systems. A single probe could, in theory, spawn an exponentially growing number of descendants, each exploring a new star system, each replicating again. Within a few million years, such probes could explore much of the galaxy. And if probes can do it, why not humans? Not traveling themselves, but sending the information needed to create humans. DNA sequences, cultural knowledge, instructions for growing embryos, for raising children, for building civilizations. A spacecraft could carry frozen embryos and automated systems designed to arrive at a distant star, find a habitable planet or moon, and then begin the process of creating a colony. It sounds like science fiction, and it is, but it is science fiction grounded in principles that do not violate physics. It is speculative, but not impossible. If a civilization takes this approach, if it is patient, if it thinks in timescales of millions of years, rather than decades, then the galaxy becomes accessible. Not in one lifetime, not in 1,000 lifetimes, but eventually. There are perhaps 400 billion stars in the Milky Way. If even a tiny fraction of those have planets, and even a tinier fraction of those planets are habitable, there are still millions of worlds where life could take hold. A patient, long-lived civilization could seed them all. But this is not the question we set out to answer. This is not about what humanity, across deep time, might accomplish. This is about you, a single person, one lifetime, and the truth, when we return to that scale, is sobering. In one human lifetime, with current technology, you could travel about 40 billion kilometers. You could reach the outer edges of the Kuiper Belt, perhaps glimpse the beginning of the Oort cloud. You would be farther from Earth than any human has ever been, surrounded by darkness and cold, with the sun a distant star behind you. With optimistic near-future technology, nuclear pulse propulsion, or fusion rockets, you might reach a few % of light speed. You could travel perhaps a light year or two. You would be in interstellar space, truly between the stars, farther from any star than from any other. You would be in the void, the empty space where starlight is faint, and the galaxy is just a faint band across the sky. With extremely advanced technology, the kind we can barely imagine, you might reach 10% of light speed. You might travel 4 or 5 light years. You might, just might, reach Proxima Centauri in your old age. That is the answer. That is the brutal, beautiful, humbling truth. 1 star, at best. But perhaps there is another way to think about this. Perhaps the question we should be asking is not how far, but why. Here's your script with ultra-slow pauses added in dot form. There is a tendency, when we think about space exploration, to measure success in distance. How far have we gone? How many light years have we crossed? How many stars have we reached? But perhaps that is the wrong way to think about it. Consider what we have already accomplished. In the span of a single human lifetime, perhaps yours if you are old enough, we went from never having left Earth's atmosphere to landing on the moon. 12 humans walked on another world. They looked back at Earth, a blue marble hanging in the void, and they saw it as no one had ever seen it before, whole, fragile, alone. That single image, the photograph called Earthrise, taken by Apollo 8 astronauts in 1968, changed how humanity thought about itself. It made us aware, viscerally and undeniably, that we live on a small planet, a delicate oasis in the vastness of space. It helped spark the environmental movement. It shifted consciousness. And the astronauts only traveled 384,000 kilometers. In cosmic terms, they barely left home. But the impact of that journey, the shift in perspective, was profound. We have sent probes to every planet in the solar system. We have seen the storms of Jupiter, the rings of Saturn, the ice geysers of Enceladus, the mountains of Pluto. We have landed robots on Mars and driven them across ancient riverbeds. We have flown through the tails of comets and touched the surface of asteroids. None of these achievements crossed interstellar distances. None of them reached the stars. But each one expanded our understanding of the universe and our place in it. Perhaps the goal of exploration is not to conquer distance, but to satisfy curiosity. Not to dominate the cosmos, but to understand it. Not to plant flags on every world, but to see them, to study them, to marvel at their strangeness and their beauty. There is a Carl Sagan quote from his book Pale Blue Dot, reflecting on the Voyager 1 photograph of Earth, taken from the edge of the solar system. Look again at that dot. That's here. That's home. That's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Voyager 1 was 6 billion kilometers from Earth when it took that photograph. In cosmic terms, a trivial distance. But the image itself, Earth as a single pixel, a pale blue dot suspended in a sunbeam, was profound. Distance, it turns out, is not the only measure of meaning. Human beings have always been explorers. We walked out of Africa and spread across the entire planet. We crossed oceans in fragile boats, not knowing what lay on the other side. We climbed mountains because they were there. We dove into the deepest parts of the ocean. We sent probes to the edge of the solar system. Not because it was easy. Not because it was profitable. But because we are curious. Because we want to know what is out there. Because the unknown calls to us. And perhaps that is enough. You might never travel to another star. You might never even leave Earth's orbit. But you can look up at the night sky and know that those stars are real places. That some of them have planets. That on some of those planets, perhaps, there is life. You can know that the universe is vast and ancient and beautiful, and that you are part of it. You can know that light from distant stars has been traveling for years, decades, centuries, just to reach your eyes. That when you look at the Andromeda Galaxy, you are seeing it as it was 2.5 million years ago, long before humans existed. You are looking backward in time. You can know that the atoms in your body were forged in the cores of stars that exploded billions of years ago. That you are, literally, made of stardust. That the universe is not some separate, distant thing, but something you are intimately connected to. Perhaps the question is not how far we can travel in one lifetime, but what we can discover. What we can learn. What we can come to understand about the cosmos and ourselves. Because in the end, we are not separate from the universe. We are part of it. We are the universe's way of knowing itself. And that, perhaps, is the point. It is night again. You are lying in the same field, staring at the same stars. But something has changed. You understand now what those lights are. You understand the distances involved, the physics, the energy, the time. You understand that if you left Earth tomorrow, if you boarded the fastest spacecraft humanity could build, you would spend your entire life traveling and reach only the very edge of your solar system. Perhaps, if you were extraordinarily fortunate, if technology advanced beyond anything we currently possess, you might reach one nearby star. One star, out of hundreds of billions. It is humbling. It is, in a way, heartbreaking. The universe is so vast, and you are so small. Your life is so brief, and the cosmos is so old. But here is the thing. You are here. You exist. You are a pattern of atoms and energy and consciousness that has emerged from the universe itself, capable of looking back at the stars and understanding what they are. You can ask these questions. You can imagine these journeys. You can dream of touching distant suns. And even if you cannot cross those distances yourself, you are part of something larger. You are part of humanity, a species that looked up at the night sky and wondered, and then built tools to explore it. You are part of a lineage that walked on the moon, that sent probes to the edge of the solar system, that peered back in time to the birth of the universe. The stars are far away, impossibly far, but we have already begun to reach for them. In one lifetime, you might travel to the outer planets. You might stand, in reality or through telepresence, on the icy surface of Europa or Titan. You might see the rings of Saturn with your own eyes. Watch them shimmer in the sunlight, vast and impossibly thin. 1,000,000 kilometers of ice and dust held together by gravity. You might help build the first fusion rocket, the first true starship. You might not live to see it arrive at its destination, but you would know that you helped make it possible. Or perhaps your contribution is smaller. Perhaps you look through a telescope and see something no one has ever seen before. Perhaps you teach a child about the stars, and that child grows up to become an astronaut. Perhaps you write a story, or create a piece of art, or simply stop for a moment and feel awe. Because that is what the stars give us. Not destinations, not conquests, but perspective. When you look up at the night sky, you are looking at distances that dwarf anything in your daily life. You are seeing photons that traveled for years to reach you. You are witnessing the universe as it was in the past, a ghostly image of stars and galaxies that may have changed, or even died, since their light left them. And you are seeing your future, because those stars, those distant suns, are where we will go. Not in your lifetime, perhaps. Not in the lifetimes of your children or grandchildren. But eventually, humanity will spread outward. Slowly, patiently, across centuries and millennia. We will send probes and ships. We will establish colonies. We will adapt to life in space, perhaps changing ourselves in the process, becoming something more than we are now. And one day, thousands or millions of years from now, there might be a human, or something descended from humans, lying in a field, on a planet orbiting Proxima Centauri, looking up at their night sky, and seeing a faint yellow star, and they will know that that star is the sun, that their ancestors came from there, that the journey took generations upon generations, an epic voyage across the void, and they will look at the other stars in their sky and ask the same question you are asking now. How far could I go? The universe is not unreachable. It is only patient. We are brief. Space is vast. Time is long. But even a brief spark can travel far if it carries within it the light of curiosity and wonder. So look up. See the stars. Know that they are real places, real suns, some with real worlds. Know that we have already begun the journey, even if it will take longer than any one life to complete. And know that you are part of something extraordinary. You are a piece of the universe that has awakened to itself, looking outward, asking questions, imagining journeys. In one human lifetime, you can travel farther than anyone who came before you, not because the technology is so much better, though it is, not because the distances are shorter, because they are not, but because you carry with you the accumulated knowledge of everyone who looked up and wondered before you. You stand on the shoulders of countless dreamers and scientists and explorers. You are the latest chapter in a story that began when the first human looked at the stars and felt that ancient stirring, that deep longing to know what lies beyond. And that story is not finished. It has barely begun. The stars are waiting, not for you to conquer them, not for you to claim them, but for you to reach them. to touch them, to understand them. And whether you travel in body or in mind, whether you cross 100 billion kilometers, or simply sit in a field and imagine, you are part of the journey. The universe is vast, but you are here, and that is enough. Look at the stars. They are far away, but they are not unreachable. Not forever. Not if we remember that the journey is not about distance, but about the reaching. Not about the destination, but about the wonder of trying. And now, as the stars continue their silent burning, as galaxies turn without hurry, as space itself expands without intention, there is nowhere you need to go. The universe is not rushing. Planets orbit patiently. Light travels steadily. Time unfolds without urgency. You do not need to cross the distance tonight. You do not need to solve the cosmos. The stars will remain, whether you look at them or not. Your body, here on Earth, follows its own orbit. Breath in, breath out. Steady, unforced. Thoughts, like distant constellations, may slowly dim, not disappearing, just becoming quieter. The universe does not demand movement. It simply continues. And you are allowed to be still. Let the vastness remain vast. Let the distance remain distant. There is nothing to reach right now. Only this moment. Only this breath. Only this quiet. As the cosmos moves on, without effort, you may also drift. Not toward a destination. Not toward a discovery. Just into rest. Within the same universe that once formed the stars and formed you. Good night, and remain a quiet part of something vast.